Alright, welcome everyone to the Unitronics webinar on Function Block Protocol. My name is Daniel Logie. I'm an applications engineer here at Unitronics. I'm accompanied today by my colleagues Mike and Alex. If you have any questions during the webinar, please enter them into the questions box. Mike and Alex would be happy to answer them. At the conclusion of today's webinar, the video of the webinar, the presentation, as well as both examples that I'm going to cover will be posted on www.unitronics.com. You can view them at your pleasure. So I'm going to begin today's webinar with a brief PowerPoint presentation. And I'm going to begin by reviewing ASCII characters. The chart before us is a list of ASCII characters in red in their corresponding decimal and hex value on the left. We see the first 32 ASCII characters are all ASCII commands. ASCII numbers begin at decimal 48. Capital letters begin at decimal 65, and lowercase letters begin at decimal 97. So it's important to note that ASCII characters are cap sensitive, meaning capital A is not the same as lowercase a. And numerical ASCII values are not equal to their decimal values, meaning 0 in ASCII format is actually equal to 48 in decimal. Just a very brief review of strings. A string is a vector of operands containing ASCII characters. For example, if we take my name, Dan Logie, this is known as a string. Each character, ASCII character, is 1 byte. If we were to separate my name into memory integers, a memory integer is a 16-bit register. Therefore, it contains 2 bytes or 2 characters. Therefore, MI0 would hold the first 2 characters of my name, capital D-A. MI1 would hold end space, and so on and so forth. It's important to note that each string ends in a null, signifying the end of a string. This is how VisiLogic realizes the string has ended. If my name only had 1 E, for example, and my name ended in MI3, MI4 would still be required to hold the null. Because again, the null signifies the end of a string. This is the only way VisiLogic realizes the string is over. If I was to separate my name into double words or memory longs instead of memory integers, both double words and memory longs are 32-bit registers. Therefore, they can hold 4 bytes or 4 characters. And we see my name separated into double words, 3 double words. If anyone is unfamiliar with strings or needs a refresher, I would recommend watching the strings webinar available on our website. And this goes much more in depth into strings and ASCII characters. Now we'll begin to talk about Function Block Protocol. It's also known as ASCII Protocol, and it allows Unitronics controllers to communicate ASCII characters or strings. The protocol is open and definable, meaning that inside of VisiLogic, we will define the ASCII messages that we are expecting to receive, as well as the ASCII messages that we are going to send. The physical layers supported are serial, RS-232 and RS-485, as well as Ethernet. Now in this webinar, I will be discussing serial communication, serial function block protocol, but the basics remain the same for Ethernet. Some common applications that may use function block protocol include a barcode scanner, a RFID card reader, printers, frequency converters, and drives. So if we have a drive that communicates ASCII protocol, we may have to send a run command to the drive or a stop command. Alright, now that concludes the PowerPoint presentation. I have prepared two examples today. The first is with a barcode scanner. For the barcode scanner, I'll be working with a V570 controller, and my barcode scanner will be communicating to the V570 over COM port 2 of the controller. Now what I'm going to do is actually demonstrate the program, and then I will explain the latter. So I'll go online with my V570, and I'll make the screen larger. And what I have in front of me is 4 barcodes. I have a barcode for my V570, a standard barcode for the V350, the V130, and finally I have a test barcode. So I'll scan my V130 barcode first, and we'll see at the bottom of the screen here, this is the ASCII message that we received from the barcode scanner. And I programmed it so that it shows a picture of the V130 when we receive this barcode. I will then scan my V350 barcode, and we see the ASCII message received updates as well as the picture. I can scan my 570 barcode. Again, the message updates as well as the picture. And finally, I will scan my test barcode. And I do not have my test barcode programmed into my V570. So we see the barcode here, and the controller recognizes that it is an unknown part number and shows a picture of a yellow circle with an exclamation point. So now that we've seen how the program functions, let's talk about the latter. In net number 1, upon power up of the controller, I'm going to initialize my COM port 2, which is where my barcode is communicating. I'm giving my PLC a name, and I'm running my function block protocol configuration. So again, SB2 goes high for the first scan of the controller's life. I'll open up my COM initialization function block. For those of you who are not familiar, it is located here under the drop-down menu. And for my COM initialization, I'm initializing port 2. And again, this is the physical COM port on the controller. The V570 can support up to 3 serial COM ports. I'm using COM port 2 on the left-hand side of the controller. My baud rate is set to 9600, which is the baud rate that the barcode scanner communicates. And I also have RS-232 selected in the upper right-hand corner. I can also communicate RS-485 as the physical layer, but it must be selected here. In the controller you're working with, it will have dip switches that need to be set for RS-485 communication. So again, this is set in the software as well as on the controller. For my PLC name, I simply gave it the name of PLC. And now we will discuss the function block protocol configuration. All of the function block protocol function blocks are located under the drop-down FB'(S). We have our configuration, our scan, send, copy buffer content, and reset buffer content. We'll talk about these one by one, starting with the configuration. This has to be run once on power up of the controller. When I open the configuration function block, it asks me to name this particular protocol configuration, and I've given it the name barcode scan. If we had 3 barcode readers, each communicating on a separate port of the controller, we would need 3 protocol configurations, each with their own name. The second parameter I have to define is which COM port the barcode will be communicating over. You see I have the list of COM ports 1, 2, and 3. Again, 3 is the max for our controllers. Currently, I'm communicating over COM port 2. Additionally, we have our function in progress bit and our status message. There can only be one type of communication over a single port at one time, so the function in progress bit will tell us when a message is being sent or received. It will tell us that the COM port is currently busy. Again, this memory bit will be 1 when there is something in progress. The status message will help us troubleshoot communication failure. Meaning for some reason, if our communication fails, there will be a status message saved into MI0. This is a pointer value. We visit the help file and scroll down to communication protocol error messages. Here are all of our error messages listed. A value of 0 stored into the given MI means the operation was successful. A value of 1 indicates a general error, an unknown system error. A message of 2 means the COM port is currently busy, and so on. So if we do experience communication failure, the first thing we want to check is this status message. And that completes the protocol configuration. Additionally, on power up, after these 3 function blocks have been run, MB5 is set. MB5 indicates that the controller is ready to scan over COM port 2. If we look in net number 2, a direct contact linked to MB5 activates the protocol scan. Now the protocol scan is where we define messages that we expect to receive. This is where we build the structure of messages. Now before I open my protocol scan that I have built, I'm actually going to cover a new protocol scan function block and explain some of the properties. Now we see when we drop the function block, the current windows appear, and we're prompted for a session complete bit. I'll link it to the next available memory bit. And this bit will go high when we receive a valid message, a valid ASCII message. This bit will be 1. Next, we must link a memory integer. And this memory integer will hold the number of bytes received in the last message, the last valid message. So I'll choose the next memory integer available. And again, that's going to hold the total number of bytes we receive in the message. Just as a side note, 1 byte is equal to 1 character. So this will tell you how many characters we received. ASCII characters, that is. And lastly, we have index of received message. If we're expecting a variety of messages, we must define them all. In this index will be a pointer value to which message was just received over port 2 of the controller. So this will be a pointer, and I'll explain a little bit more on this in a moment. So these are universal operands for the scan function block. In the top right-hand corner, we must select which protocol or which port we're working with. Currently, we have 1 protocol defined, which is barcode scan. But again, if we were working with 3 barcode scanners, all of them would be named something different, and we would have to select from this list which barcode scanner we are referring to. Next, we have 2 main types of messages that we can receive. We have static messages and variable messages. We'll begin with variable messages, or actually we'll begin with static messages. And let's take an example of a drive. Now the drive is sending our controller a ASCII message. And let's say it's going to say run. The word run is going to be sent to the V570. We simply define run as our message in row 0. We can add a message. We can insert a message before the current message or after. I'm going to insert a message after. And it's just going to alert me that the new message will increment by 1, which is okay. So now we have message 1 that we're scanning for is run. And the second message, so we're scanning for stop. So we have run and stop. And again, these are called static messages. Now let's say we don't know what the message is going to be incoming from our theoretical drive. We're not sure what the message is or the message length. What we can do is insert an additional message, and we can now define a variable. Variable is defined here. Create/edit new variable. And you'll see I have 3 tabs for 3 different options, 3 different variables. I'm going to start with stream because it is the most basic. A stream is going to read the incoming message and store it in ASCII format to an operand. So again, it's going to read the incoming string and store it in ASCII format. First, we're going to assign a link, which is where we would like the message stored. I'm going to store it in MI600. I'll give it the name received message. Now returning to the top of the window, it's going to ask us to set a vector length. This will be the number of operands we would like to receive for the incoming message. If we had a message of, let's say, 10 characters incoming, 10 or less rather, we can set 5 operands because, again, 2 memory integers, or 2 characters per memory integer rather. So a memory integer can hold 2 ASCII characters. The next option we have is to convert one received byte to one linked element. To clarify this, it's basically saying convert one character, one ASCII character, to one memory integer. Now, as we just clarified, a memory integer can hold 2 ASCII characters. So from the drop-down menu, I have the option to select convert 2 characters to one memory integer. This is the more commonly used option. It saves memory inside of the controller by using less memory integers, and it also keeps the string together. There are certain cases where one received byte to one linked element is useful, but again, the majority of cases would be to convert 2 bytes to one linked element. So now again, we have a vector length set to 5, which means we can accept a message up to 10 characters long. Finally, we have an additional option here to add a null to the end of a string. This means we are adding a null to the end of a message. And as we covered in the PowerPoint presentation, a null signifies the end of a string in VisiLogic. So if your device does not already add a null, we can do it here manually. And you see our variable is defined when I select OK. Now any message that we receive that is 10 or less characters long will be stored into MI 600 in ASCII format. So we do not need to know the incoming message or even the structure. The length does not matter. If it's less than 10, we will be able to read it. One additional note I would like to make is we have MI selected currently. If I select a 32-bit register, such as a double word or a memory long, we mentioned in the PowerPoint that these are 32-bit registers that can hold 4 total bytes, 4 characters. Right now we're converting 2 bytes, or 2 characters, to one double word. You see from the drop-down menu, we now have the option to convert 4 received bytes to one linked element, one double word. Again, this is a space saver, and it also keeps the string together. So this is the more commonly used option when working with double words. Okay, that covers a stream variable. Now we can talk about a numeric variable. Now a numeric variable is mainly used when we're working with numbers in ASCII format. Now let's assume we have 555 in ASCII format. If I refer back to my PowerPoint, a 5 refers to 53 in decimal. So if we read in a 555 decimal ASCII, and we store it into a stream, this number is not ready to be used in VisiLogic because, again, it is still in ASCII format. In decimal, it is actually 53, 53, 53. So what the numeric option does is it takes the incoming string, 555, that is in ASCII format, and it converts it to decimal for you. If we refer to our chart again, 555 in ASCII is converted to 555 in decimal and stored in a memory integer, a single memory integer. So it's 555 inside of a memory integer. Now we have a function block in the ladder called ASCII to num that will accomplish this, but this basically eliminates the need for that step. Again, it's going to take ASCII characters, ASCII numbers, and convert them to decimal format. Now we have several options in this tab. If we know the length of the incoming variable, we can select it here, fixed length. If I knew that a vector length was 1 operand long, it would hold 2 characters. We can also choose no fixed length, meaning we are unsure how long the variable will be, the incoming variable. Next, we must select a decimal point. If the incoming string has a decimal point in it, that must be removed, because as all of us know, memory integers, memory longs, and double words do not work with decimal points. They work with whole numbers only. So we must tell the controller where the decimal point is in the incoming string. So I'll assign the next memory integer, and I'll name it decimal placement. I'll give it a power-up value. Now let's say we have a 2 stored into MI31. This means that the decimal point, or decimal placement, in the incoming string is in position 2. If we have a 3 stored into MI31, the decimal placement for the incoming string is in position 3. If there is no decimal for the incoming string, we simply enter a 0 into MI31. Our last option here is the prefix sign format. If our ASCII message is coming in with a positive or negative prefix, we have to tell the controller that so that it can either remove it or include the negative. If there is no prefix for the incoming message, we simply select no prefix. Lastly, I would like to discuss checksum. Now, a checksum is essentially an integrity device or integrity test for the incoming message. It is sent by the third-party device. Many devices don't require a checksum, some do, and sometimes it's optional. This checksum will be defined in your device's documentation. A sum8 is a very popular checksum, as well as a CRC8 and a CRC16. And we support various types of checksums. But again, this will be defined in your third-party device's documentation and must be defined here. And to reiterate, it is an integrity test for the message. It ensures that the incoming message is correct and there was no noise or interference with the message. Next, I would like to talk a little bit about start of text. If my incoming message from my barcode scanner starts with a character, ASCII character, I can define it here. Again, we can choose 1, 2, 3, or 4. I simply double-click on the white space here, and I can choose what character is my start of text. Let's assume that my barcode scanner reads in the barcode and begins the message with a pound sign. I can simply select pound here. And the message that I'm looking for is pound, and then one of these 3 messages. Pound run would be acceptable, pound stop, or pound variable. If I had more than one character for start of text, I can simply define an additional one. Start of text is not required either. Some devices do not send a start of text. Next, I'll discuss my terminators, beginning with end of text, which is much like start of text, simply a character that defines the end of the text, tells the controller that the message is over. And again, I can double click, and I can scroll down, and let's assume that my message ends with a plus sign. And a star. Now, if our third-party device sends the message run, this is not a valid message. We have programmed an end of text. We must receive the message run plus star. It's also worth noting that if we define an end of text, we want to also use our checksum here. So again, if we do not have an end of text, we can include our checksum after each message. But if we do have an end of text, we can include our checksum with the end of text. Either we can have our checksum and end of text, or end of text and then checksum. If our third-party device does not send an end of text, signifying the end of a message, we have two other options that we can use. We can use a message length in characters or bytes. So if I select a message of 10, the controller will be looking for ASCII messages that are 10 characters long. So a run would not be a valid message. Stop would not be a valid message. However, my variable here that is 10 characters long would be a valid message. So this applies for all messages built above. Finally, we have the option for silent duration. This is measured in milliseconds. When the controller does not receive additional information after this set amount of time, it assumes that the message is complete. Currently, I have 10 milliseconds selected. Can go all the way to 1 up to 2000. That pretty much covers the scan function block. Let's take a look at the scan function block that I have built. Again, in the top right, I have my barcode scan selected. My barcode reader sends a message with a start of text, and it sends decimal 2 hex 2 start of text as the start of text. I then have 4 total messages, 3 that I am aware of, my 570, 350, and 130 barcodes, and I have a variable message. Now before I actually get the barcode, which is pound V570-57-T20B, I have programmed my barcode scanner to send a scanner number. If I double click on this variable here, I'll see that it's a numeric. It's a fixed length decimal ASCII. It has a vector length of 1. And it is a single numeric value when it comes in. And it's stored in MI3. Now this scanner number is present before each of my messages. Finally, I have my variable, which is going to read any barcode that is not one of the above three. I have a vector length of 7 set, which means 7 MIs are reserved, totaling 14 characters. So again, I'm putting 2 bytes into one linked element, I'm adding the null, and I'm storing it into MI50. It's important to note how the controller recognizes messages. The controller is going to begin at the top and work its way downward. So if I scan the first barcode in the list here, the controller will recognize it is, in fact, this barcode, and it will not travel down the list, even though this barcode would also fit into my variable. Again, it doesn't get that far because it recognizes a valid message above the variable. We want to keep this in mind when we are writing our incoming messages. We don't want to put our variable at the top. Now lastly, my barcode scanner has end of texts. It actually has 2 characters signifying the end of text. It is, which one was it? It was 0D and 00. So 0D is a carriage return, and 0A is a line feed. So when it recognizes these 2 characters, the controller that is, it realizes that the message is over. Now quickly referring back to the index, MI2, if I receive my first barcode scan, my barcode message defined here, it will have a 0 stored into MI2, a 1 for the V350, a 2 for the V130, and finally a 3 if it is my variable. So again, let's keep that in mind. My index is MI2. I'm now going to go to the display. And this is a list of images by pointer. The icon can be found here, list of images by pointer. And I have a total of 4 images, starting with my 570, 350, 130, and finally my invalid message. And my pointer to these images is MI2, my message index. Now referring back to the ladder, once I receive a valid scan, the session complete bit goes high, and I'm actually incrementing MI6 off of the session complete, which is counting the total messages received. Additionally, off of the session complete bit, I'm working with my buffer. Now each function block protocol, each port is going to have a buffer. It's going to hold the last message that we received. Now good programming practice is to use the copy buffer contents and reset buffer off of the session complete bit. So what we're doing with the copy buffer is we're copying all the contents of the buffer to MI100. Then we are resetting our buffer so that it is ready to accept the next message. This way that our previous message, the contents, is stored into MI100, and we can view that if we wish. Additionally, in rung number 5, I'm comparing MI2, which again is my index of my scan, which message I just received. I'm comparing that to a value of 3, which is my invalid or variable message. if MI2 indeed equals MI3, we are setting memory bit 3. We're not setting, but energizing memory bit 3. If I revert back to my display, memory bit 3 actually triggers a binary text. See memory bit 3 here. It is blank when off, and when on, we received unknown part number. So again, when we scan a variable, not one of our 3 valid messages, the unknown part number displays on screen. Okay, a few more things I'd like to discuss in this example. This is my ASCII string here. ASCII string is located here in the HMI elements. And if I open up the element, we see MI100 is the start of vector for the string, which is my buffer contents. So whatever message I just received, I'm going to display that on my screen. It has a max character length of 30. And lastly, let's talk about our scanner number. Going back to the ladder and opening up the scan, we're going to discuss our numeric variable in front of each message. We see them all linked to MI3, which is our scanner number. And again, it is numeric, so it's converting the ASCII to numeric for us. Viewing our HMI display, this variable is a numeric, and it is linked to MI3, which is our scanner number. So I'd just like to demonstrate the program one final time. When I scan my first barcode, which is the 570, it receives the message here, which is in ASCII format. We define the 5 as a numeric variable, so it converts this ASCII 5 into a numeric 5, and I'm showing this 5 on display. Also using the index pointer value of this message to show the V570. I'll do the same for the V350, the V130, and finally my fake code. And that covers the first example that I prepared for you today. Now I have another V570 on my desk. With an alternative BizLogic project stored into it. And what I'm going to do first is actually open up a software called Hercules, which is available for download on the web. And this can simulate a third-party device that communicates ASCII. So I'm going to go online with my second V570. I'll make the screen larger. And actually, I'll pull this aside. Place Hercules right next to it. And I'm going to click on the tab Serial. And I have my information here. I'm connecting over COM port 4. This is my computer's COM port, not the COM port of the controller. I'm actually connected via COM port 1 of the controller. My baud rate is 9600 baud. and I will open the connection. My connection is now open. Now my program in my V570 is set up to both send and receive a message. So I can send a message to the V570 from Hercules. And I can also send a test message from the V570 to Hercules. And we see test message appear. We also see the total messages being sent incrementing. So again, I could change the sent message to run, change it to Excel, and my V570 will accept the ASCII message that I'm sending. I could even send it a 555, and it's going to accept the message. Again, by pressing the send test message, I can send a test message to Hercules. Now let's take a look at what's going on in the ladder to make the V570 function as such. Now, this is very similar to the last example. Upon power up, giving my PLC a name, I'm initializing COM port 1 of the controller. This is the physical COM port. And you see that my baud rate is 9600, which was just set up in Hercules. And I'm running my protocol configuration on power up, giving it the name ASCII, and informing the controller that it will be communicating over COM port 1. Scrolling down to the scan function block, I am accepting one message, and it is a variable message. It's a rather long variable message. By doing this, I'm telling the controller essentially to accept any message that is being sent as long as it's under 60 characters and store it into MI20. Should be adding a null at the end of the stream. So again, this is set up to accept any message, any ASCII message that is under 60 characters. We see my terminator is silent duration. I'm waiting 10 milliseconds if there is no additional information or communication. The controller knows that the message is complete. Now I mentioned that my stream is stored into MI20. MI20 is shown on display as an ASCII variable. MI20, and actually here I'm only accepting a length of 30 characters. I can actually be accepting 60 characters. Scrolling down, in net number 3, when the session is complete, I am resetting the protocol buffer. Since we're storing all messages into MI20, there's no real need in this example to copy the content of the buffer before we clear the buffer. Now, nets 4 and 5 are introducing some new function blocks that we did not cover in the previous example. MB1 is actually the button on screen, send test message. And when we press the button on screen, we are going to set MB2, which then closes this contact and sends a message. Now the reason that we have communications set up so that when we push on the button, we set a bit, is so that if there is a function in progress, this command will wait its turn until the function in progress is complete, then send the message, and then finally reset MB2. If we simply had a button linked to a positive transition here, and there was something in progress, then the message would never be sent. Now we can open the protocol send, and we see that I have a static message here, test message, that was sent to our Hercules software. Now if I were to add a message, notice down here there is nothing currently. If I were to insert a message, we now have message 2, and we are asked for a message number, which is going to be a memory integer. Depending on what is inside of this memory integer is the message we will send. If a 0 is currently entered into memory integer 6, send message test message. And if a 1 is stored into memory integer 6, send the message in row 1. Now we see a static message here. This is very simple to set up. Simply with your keypad, enter test message. What I would like to cover is a variable message. And again, we're going to use the same icon that we used in the protocol scan to create a new variable. And we have some additional content here. First, we can send binary text. Essentially, we're linking a memory bit 7, and we can send, for example, run if the memory bit is off when we send the message, and we can send stop if MB7 is 1 when we send the message. So depending on what memory bit 7, the status of memory bit 7 when we send the message, we can send 2 different messages. Moving on to numeric, we're going to link memory integer 9, and there's going to be a number in decimal format stored into memory integer 9. What this function will do is it will take that number, convert it to ASCII characters, and send the number in ASCII format. Again, we have a vector length, which is the total number of memory integers that we would like to send. It's going to give us an option to include a decimal place in the message, because again, there is going to be no decimal point currently in MI9, whatever number is inside of MI9. We can include the decimal point. We can include leading zeros or spaces. And we can also include a prefix. Excuse me. Moving on to a stream. This is a message that is already built. So I'm going to call this ASCII message. And we have the same option here. Convert one linked element to 2 send bytes. If we were to choose this one, it would convert one element, one MI, into one send byte. So if we have 2 bytes or 2 characters stored in the MI, we want to choose to convert one linked element to 2 send bytes. Now we can define the vector length here. It can be either direct or indirect, meaning direct if our vector length is always 5 characters long, or indirect, we can link a memory integer, and depending on what is stored in that memory integer, that is the length of our message being sent. The next option is a list of text. And we can have 3 or 4 or 5 different messages. And we link a memory integer. This is going to be our pointer. Depending on what is stored inside of memory integer 12, one of these 3 messages will be sent. If a 0 is stored, run will be sent. If a 1 is stored, stop. And if a 2 is stored, excel. Next, we have a checksum, which we discussed in the previous example. We can send our date in various different formats, and we can send our time. Now, much like the scan, we can also include a start of text and end of text for the message. And lastly, I would like to point out the option for advanced here. We can send data destination, check that. And essentially what this is going to do, this is going to act as an outgoing buffer. So first we need to link a memory bit that is set to enable this feature. And we can copy the contents of our send to a memory integer. Now the information that we send will be copied to MI1000. Again, we need to convert one linked element to 2 send bytes. Now each time we send a message, we can store MI1000, let's say, to a data table, and we can keep track of all outgoing messages that were sent from the controller, just as an example of one of the many uses of this function. Well, that covers everything that I had prepared for you today. If there are any questions at this time, please enter them into the questions box, and I would be happy to answer them.